Hello, we are Team 15, and we will be presenting our analysis and redesign of CPU cooler. About the CPU cooler, the CPU cooler is widely used in computers and laptops for long periods of time. How it works is a compact motor drives a series of fan blades, which propels air to dissipate any heat generated by the CPU. The design allows for precise temperature regulation and prevents overheating. So our target customers, we identified two main groups of customers. Our primary customers are companies that produce laptops and computers, and our secondary customers are data processing companies, PC builders, and gamers. The global market size is also about $10.5 billion. Here is our exploded view of our CAD model showing all the components and the quantity of components. Here is our fast diagram, which describes the function that the CPU cooler must perform. As you can see, the primary function is cooling the CPU. Here we have the function component mapping matrix. It shows how the functional components correspond to the leaves in the fast diagram. All the components have 1 to 2 functions. The secure components function requires the most components to work, which can indicate a potential redesign. As mentioned earlier, there are different groups, different product group, different customer groups, and each group has slightly different needs, mainly preventing injury, allowing flexibility, and varying speed. Using the function component mapping matrix, we identified module parts that we can change between the two different product variants. Here is our CAD design for the primary customer group and the secondary customer group. And here is the common interface between the two variants. The module components of each variant plug into the same holes in the base platform. Here is our feasibility assembly sequence. You can see the original and modified assembly sequences. The modified sequence places the integration of the circle clip and the spring before the fan. This better optimizes delayed differentiation and therefore optimizes the assembly sequence.
We analyzed the assembly and found the highest impact parts on the manual assembly time. 4 types of things significantly increase the manual assembly time, so that's the first thing we want to change. Then we found the opportunity to combine the fan fixed spring and fan holder to shorten the time. The original fin design takes 220 seconds to assemble. We improved the design for manual assembly by decreasing the part variety from 4 to 1. We also added some features to increase part symmetry, facilitate orientation, and provide locating features. There's no major effect on the part function. Also, decreasing in the cost due to the less molding needed. Assembly time was reduced to 212 seconds. As we can see, the fan fixed spring and the fan holder shared the same functions to prevent injuries and ensure fastness, so we try to combine those two parts. It takes 22 seconds to assemble the fan frame, including the fasteners. By combining the two parts, we can eliminate fasteners and use snap fits. Assembly time was reduced to 3.5 seconds. There's no major effect on the part function, but we changed the way to fix the fan frame. We saved the cost for the fan fix frame, but added 2 extra clamps.
For automated assembly improvement, we select copper tube A, B, C, and copper plate. Those components were in the bottom quadrant of the car chart, and the function component mapping matrix identified as 3 copper tubes share all functions, which was a strong indicator for the opportunity for part variety reduction. Those figures show the original design in their exploded CAD. The total handling and insertion cost of the assembly before redesign was $13. This figure shows the modified design. We reduced the part varieties of copper tube from 3 to 1 and made it symmetric to assist in automated fitting. Also, steps are added on both sides of the tube to facilitate orientation. For copper plate, grooves and clips were added to the top half, and the bottom half perimeter was shaved off for easy insertion and locating. The improvement resulted in a cost reduction from $13 to $3.3, a 74% reduction. The change had no effect on part function, but would impact manufacturing costs due to decrease in copper tube cost and increased cost for machining the copper plate.
Here is the process selection for the aluminum fin. Its major function is to reject heat. Here are major dimensions. And based on standardized feed hole requirement and part parameters, the tolerance is 0.005 inches. Locations and dimensions of the fin mounting holes are critical to ensure a good contact with copper tubes, which further ensures a good ability to reject heat. In the next page, based on aluminum material, shape, mass, thickness, tolerances, surface finish, and economic batch size, we came down to sheet metal working and machining. We finally chose sheet metal working because it has higher material utilization, consistency, and repeatability, and it is more cost efficient for producing large quantities of parts than machining.
When looking at redesigning the fin for manufacturing, DfM Pro was used to identify any concerning elements in the original design. However, none were found when using this tool. The original cost using hubs was found to be $2.66 per part. When thinking of redesigns, there were three major rules that were considered. First, sharp bends were removed from the tabs in the original design following DfSM Rule 8. There was also bend offset included, which was not previously added, again, following DfSM Rule 9. Finally, following DfSM Rule 4, the part, due to previous changes made, was using cutoff over blanking method to manufacture the part, and also the overall length of the part was reduced. These changes did not result in any major effect on the part function. However, the cost estimation of the new part came out to $2.45 per part, resulting in a small change in the cost.
Here is the process selection for the ABS fine holder. Its major function is to prevent injury and ensure fastness. In the next page, here are the major dimensions, and based on standardized feed hole requirements and part parameters, tolerance is 0.0118 inches. Locations and dimensions of 4 mounting holes and the central pillar are critical to ensure the case can firmly secure fans in place and hold the fans to further ensure protection from injury. Based on ABS material, shape, mass, thickness, tolerances, surface finish, and economic batch size, we came down to injection molding and machining. We finally chose injection molding because it is more cost efficient for producing large quantities of parts than machining. Then secondary processes is needed because the injection molding part needs to be assembled with 2 metal fan clips for the complete fan holder.
Similar to the fin, we use DfM Pro to analyze the fan holder and identify features that needs to be changed. Screenshot of the DfM Pro are shown to the right. Using the hubs cost estimator, we estimate the cost to be $1.36 per part. Based on the design for manufacturing guidelines, we redesigned the part without impacting the part function. First, we made sure that wall thickness is uniform. Then, based on DfM 3 and 5, we added a draft angle and kept the rib thickness as 60% of wall thickness. Although there is no major change in the function and cost, we saw a 34-cent decrease in the cost per part.
Here's our product service system. So we plan to offer services to improve customer experience and reduce environmental impact. For customer experience, we plan to provide repair services and warranty, including assembly manual, and as well as get feedback to change future models. And then for environmental impact, plastic and metal parts that can be disassembled and recycled. And we also want to use materials that are long lasting. To summarize, after a redesign of the CPU cooler, we reduced manual assembly time for the fin by 8.25 seconds and the holder by 19.05 seconds. We improved the automated assembly cost of the copper tube and plate by $9.72 per assembly, and we added DfM guidelines to reduce the cost of the fin by 21 cents per part and the holder by 34 cents per part. As far as critiques go, we want to perform DfM for other parts and add features to stabilize the copper tube. And if we were to start over again, we would choose different parts to analyze and try to improve efficiency.